Aloha, my Gen Chem 1. How are you today? I hope everything is going well. I hope you're enjoying your Friday afternoon. I want to start the rest of our Unit 3, and I kind of goofed up and called this Unit 4. My other classes are in Unit 4. They have more units, so I got all confused. Anyway, we are starting the second half of our Unit 3, and I love it. So the first half of Unit 3 is moles, tons of calculations. I've got all those videos done and up on your YouTube. And then now we're going to start classifying those reactions. So it's almost like we're taking, in Unit 3, we're taking what we've done already and we're just expanding the heck out of it. We're taking something simple like a molecular formula and we've just expanded it to one massive math problem in our mole section. We're going to expand it even more in our classification section where we're going to figure out what kind of reactions are happening. We're going to have sort of a couple general reactions that we're going to learn. We're going to start with one of my favorites, and that is a redox reaction. I know a lot of you are aiming towards tracks with a lot of biology. You will absolutely see your redox reactions in your biology classes. For those of us in chemistry and physics, we also see those quite a bit in batteries, in anything that is giving us electricity. Anything that has a nice flow of electrons and a flow of energy, we see our redox reactions. So they're a pretty big classification of reactions. Let's go through and define them. Just like our last section, I'm going to start with just our names and words. I love it, just to get us used to writing all of that out. So let's just write out this reaction. It's one we've seen before. We're going to take sodium and we're going to react it with chlorine. Only now we know these are our diatomics. That is Cl2. Okay, we just learned that in our moles section. And then what are we making? We know from our Unit 2 that we make sodium chloride. And how do we know that those go together? We know that sodium is going to give away an electron and chlorine is going to take it. And that is our fixed ratio. That is set by Mother Nature. That is not set by the amounts of what you add. That is set by those electrons flowing. And so this is perfect because that's what a redox reaction is. So I want to work my way through defining what a redox reaction is and work my way through just classifying this reaction. And we just learned in our last section with our units and our moles, okay, what do we need to do next? What's missing? Well, this reaction is not a true equation yet. We have not balanced, so we are still balancing everything for the rest of the semester. Remember, you have trust issues. You do not trust me to balance anything. So let's go ahead and take a second to balance this reaction. We've got 2 chlorines and a sodium on this side, but only 1 sodium and 1 chlorine on the other side. So we already know we're going to have to add a 2 in there somewhere and then balance with a 2 right there. Okay, so already we've got a nice story for this reaction. Let's add to it. Okay, the first thing I want us to add to it in order to define a redox is I want to add oxidation numbers. So I feel a list coming on. Number 1, we drew our formulas. Okay, number 2, we balanced. As of today on, number 3, I want to see those oxidation numbers. It's how we're going to classify reactions. So we already have them here. Awesome. We're good at them because we did that in Unit 2 in order to put those 2 elements together and form that ionic bond. So let's add to that concept. So in this unit, we're going to add oxidation numbers to everything. We're going to add them to elemental forms and covalent bonds. So it is not just ionic anymore. We started with just ionic, but now we're going to add in our elements and we're going to add in covalence. So that's going to be a little bit new. I'll show you how to do that. All right, so we already know the +1 and -1. That's our electrons moving while we bond. Remember, that's our electron keeping or our bookkeeping for electrons, these add up to, they balance themselves out. We don't have an overall charge anywhere. That is neutral as a compound. So, but that's as it's bonding. So sodium, before it ever bonds, it still has that electron. So the oxidation state of the elemental form of sodium is 0. You haven't bonded yet. Sodium hasn't given anything away or taken anything yet, so that oxidation number is 0. That is the same for chlorine. In fact, all of our elements in their elemental form, meaning if it's diatomic or anything, in that elemental form, your oxidation number will be 0. Okay, I love it. That is one of our most common mistakes, though, on this next test. So write that down on your cheat sheet for sure and highlight that sucker. In fact, let's sparkle pen. Okay, so anytime you're in the elemental form, your oxidation number is 0. And then we know how to do our oxidation numbers in our ionic bonds because we've already done that in Unit 2. All right, so what does that tell us? Well, that is our first definition. Let's give ourselves some space here. That is our first definition. If your oxidation numbers change, so if those oxidation numbers change from one side of your reaction, from your reactant side to your product side, did they just change? Then you have a redox reaction. So indeed, our oxidation numbers did change. We have zeros over here and plus and minus 1 over there. Absolutely changed. That means electrons were flowing in this reaction. This is a redox reaction. Okay, let's get a little bit deeper even, and let's spell out what redox means. Let's take the things that are changing. Let's start with sodium. All right, sodium is literally going from a 0 oxidation number to that +1 oxidation number. So think back to our Unit 1. What does that mean? Sodium is starting with how many electrons? Look at your periodic table. You've got 11 there. And then sodium is giving 1 away and ending up at 10 electrons. So what we add in this unit, if sodium went from 0 to +1, it just lost an electron, okay? Now, no matter what, we will write this out for each one of these reactions. We are going to track those electrons. So in this case, sodium is losing an electron, all right? Its partner is chlorine then. Your chlorine is going from a 0 to a -1. The only way to do that is to take an electron. All right, so this is the basic definition in a redox. We're going to keep adding to that. So you know from our Unit 1 history of the atom, we didn't even discover the electron until after a whole lot of studies with electricity. An awful lot of chemical reactions were being studied before anyone even understood the movement of electrons. So we have old vocab with reactions like this and new vocab. So to a chemist, we start here. We track electrons. That's the ultimate definition of what's happening in these reactions. But in biological processes, you often add the older terms. And if something lost electrons, it was being oxidized. And where did that come from? Typically, you were taking something and lighting it on fire. And if your mass went up, you added oxygen and you were being oxidized. Okay, so that's an old term, but it's still used quite often. So anytime you're losing electrons, that sodium is being oxidized. But our redox reactions always happen with partners. Okay, you don't walk up to your reaction and get a shock every time you touch it. Electrons are flowing, but they're flowing within the system. They are not flowing out to you. So you always have to have a partner. So if something is being oxidized, it's giving away an electron. That electron has to have a place to go. So that place to go then is our chlorine. So we always have vocab for both. So our sodium is being oxidized and it is doing the reducing. It is called a reducing agent. So now watch the terms for our chlorine. Our chlorine is exactly opposite. Our chlorine is gaining an electron. It is being reduced. See, there's our partnership. One is oxidized, one is reduced. And the only reason that can happen is the other one is there. So this is our oxidizing agent. All right, now write this on your cheat sheet because it doesn't change. They always stay together. So if you could figure out if you're losing electrons, that will always be oxidized in the reducing agent. Same goes for if you're gaining electrons, you will always be reduced in the oxidizing agent. So I start always with these. The rest of it is vocab, and it just goes along with it. Put it on your cheat sheet or commit it to memory. Typically, you hear these terms in your bio classes, so I wanted to make sure that we define those. All right, so in this whole process, we have electrons flowing. They are going from sodium to chlorine. And what we just wrote out was the beginning of a half cell. Now in Gen Chem 2, we will write a full half cell. We will do electrochemistry, and it's super fun. And we'll draw those cells, but this is the beginning of that. We're drawing that half cell and defining each one of those. So this is a redox reaction. And where does that term redox comes from? Now you can see it. It comes from reductions and oxidations. That's where that term redox comes from. So I love it. All right, let's do another one of these. And it is okay for reactions to be redox and something else. A reaction can be just a redox reaction, or it can be something else. I like to always start with redox or not redox. So this reaction is a redox. It also happens to be two other kinds of reactions. So let's take a second to spell that out. Our sodium is in its elemental form. Our chlorine is in its elemental form, and we just made a compound. Now this will be important in our next unit for thermochemistry and thermodynamics. And what this type of reaction is called a formation. Oop, got a little crazy with my writing there. If you've got elemental forms as your reactants and they are combining and forming a compound, this is called a formation reaction. Now, a formation reaction is a heading under a large class of reactions, which are combination reactions. All right, let's delineate between all of these. Formation is when you have elements on your left-hand side, on your reactant side. You have only elements on your reactant side, and then you're making a compound on your product side. That is a formation reaction. Okay, and we're going to see that in thermochemistry. That's important because the only thing changing in that entire reaction is you are going from elements to that compound. The only thing changing is bonding. And now we can judge the energy of that bonding. Now, this entire class of reactions is called a combination reaction. And here's how I remember it. We have only one product. You took a bunch of stuff and stuck it together and you get one compound out or one product. So how do I remember combinations? One product. Okay, I love it. All right, let's do the same process again. This is a lot of vocab. So let's do another example. And our other example, let's see if we can figure out what that is. All right, let's take hydrogen. H2. React it with oxygen, O2, and let's form water. Okay, I love it. All right, let's go through our process. We just wrote out our formulas. Now we're going to balance. So let's find our balance. I'm going to put a 2 there, and then I'm going to put a 2 right there. Perfect. All right, now what's number 3? Oxidation numbers. All right, now before you yell at your screen, hang on a second. Now, this is the fun part. what was the difference between sodium chloride and water? Sodium chloride was ionic, and we already know how to do those oxidation numbers. Our covalent compounds, we can also use oxidation numbers when we're evaluating our redox. All right, we don't necessarily use them in bonding like we did for our ionic compounds, but we are going to use them to figure out if we have a redox. So let me give us some rules. All right, elemental forms are still 0. Look at that, hydrogen, oxygen, elemental form. That oxidation number is 0. But now what the Sam heck do you do with water? Well, we're going to follow one basic rule. Find your most electronegative element. All right, we know that is oxygen. You could double check that on your periodic table if you want to. That is our most electronegative. That element will follow its rules. So if oxygen is bonding in an ionic bond, what is its oxidation number? -2. It will follow that rule. It's the strongest element in that molecule. So then hydrogen has to fit that. So if this is a -2, and remember everything is still got to be neutral, it's got to add up to 0, what does hydrogen have to be? +1. Okay, so double check on your periodic table so you know I'm not messing with you. You should have the option of a +1 on your hydrogen, and you do. Okay, perfect. So now that we've done our oxidation numbers, is this a redox reaction? Did our numbers change? Absolutely. Let's spell it out. Our hydrogen. Hydrogen went from a 0 to a +1. That absolutely changed. Did that mean hydrogen gained an electron or lost an electron? It lost an electron. Okay, then the rest of it is just flare. So if it lost an electron, that means it was being oxidized and it's the reducing agent. Okay, I love it. All right, what's the partner to that? Oxygen. Our oxygen went from a 0 to a -2. So then it had to gain electrons to do that. Anytime you gain electrons, you are being reduced and you are the reducing agent. Okay, I love it. So this is absolutely a redox, and these are your half cells. So what kind of reaction is it? It's a redox, but is it also another kind of reaction? Yep, it is exactly like the reaction on our last slide. Our redox reaction, look at this, element to a compound. That is a formation reaction. And then anytime it's a formation reaction, we've got one product here that is also a combination. Okay, I love it. So we've got 3 types of reactions, all with that one reaction. All right, let's do another one. This is so much fun. I feel like we should do another one. Oh, now we're getting a little sassier. Let's do it. All right, lead sulfide. Grab your periodic table. What in the Sam heck is lead? That is Pb. Sulfide, that is sulfur as our minus. This is an ionic bond. How do we figure out how many of each one? Well, this goes back to unit 2. What's your oxidation number for sulfur? -2. So then what about lead? Do we have +2 as an option? Yes, we do. And in fact, on some periodic tables, +2 is the only option. If your periodic table happens to have 2 of those options, we probably should have said lead 2 sulfide. It depends. Usually lead can do both, but sometimes the +2 is the only one listed. Okay. Reacts with oxygen, elemental oxygen. Let's just go ahead and put that in right away. That's a 0. And we're going to form lead oxide. Okay. So again, We should have probably called that lead 2 oxide in case I just happened to notice that I grabbed an older periodic table and I've got both of those options on there. And then sulfur dioxide. All right, let's go ahead and use our trick for covalent molecules. What are those oxidation numbers? Between sulfur and oxygen, which one is the most electronegative? Oxygen. So oxygen will follow its rule, -2. Okay, so holy crap, what does sulfur have to be in order for all of that to cancel and be neutral? Well, it's going to have to be a +4. We'll shut the front door, take a minute and check your periodic table. You have a crap ton of options above sulfur. Is +4 one of them? Yes. Okay, I love it. So is this a redox reaction? A little bit of a mystery. Do we have any oxidation numbers changing? We do. We do. Are they all changing? No. In fact, look, lead is staying the same, but check this out. Sulfur is changing and oxygen is changing. Okay, so let's write it out. So let's spell out sulfur is changing. Sulfur is going from a -2 to a +4. All right, let's just go ahead and write what that is. So if you're going from a -2 to a +4, is sulfur giving it away for free, or are you taking electrons? Literally losing electrons. That is the only way you can go from a -2 to a +4. All right, then what's our other partner? Oxygen. Okay. Oxygen is going from 0 to -2. So the only way to do that is to gain electrons. You always have to have something in your redox lose and something gain. Can you have 2 elements lose electrons and 1 element gain? Absolutely. Can you have 3 elements lose electrons and 1 element gain? Absolutely. But you have to have at least one of each. You have to have a flow of those electrons. So somebody's got to give it away and somebody's got to take it. All right, and then if we want to add our vocab to this, anytime you lose electrons, you're being oxidized and you're the reducing agent. And then anytime you gain electrons, you are being reduced and you are the oxidizing agent. Okay, I love it. So now, is this redox another type of reaction? Well, let's see. We have an element here, but this is not an elemental form. So that can't be a formation. So no formation. And then on our product side, we actually have 2 products. So that is not a combination. So this reaction is just a redox. And that is totally okay. It is okay for reactions to be only redox reactions. That is one of our main headings, and that is totally okay. All right, I wanted to just have one video that just defined a redox, and then I'm going to stop and we'll have a next video that has more redox and combination for